In this video, we show how to apply the first law of thermodynamics to a specific case of an isothermal gas expansion. Alright, so the idea here would be to have a gas inside a cylinder, and then we're going to be trying to get some work out of this gas. Right, so here's your gas, that is your initial volume, V sub I, then you have an initial temperature, T sub I, and then the idea, it's a gas, and then the idea is that this gas is going to expand. Okay, so the volume of the gas is going to increase, but an important thing here is that the temperature stays constant. So this is an isothermal process. Okay, so this is going to be the same temperature as you had before. Okay, you're doing this expansion against a constant external pressure which doesn't change. Okay, so that external pressure that you're pushing against will not change. Alright, so the question is, how do we calculate work and heat and the change in energy for this particular isothermal gas expansion? Right, so something that is important about ideal gases is that the average energy of an ideal gas only depends on the temperature, right? Using arguments that we developed in the first semester of the course, we actually saw that the average kinetic energy for an ideal gas was only dependent on the temperature, right? And that is Boltzmann constant, and that is the temperature. This is the average kinetic energy. An ideal gas doesn't have any potential energy because those molecules we're assuming that they are not interacting. So all of the energy essentially is coded by this expression. But here's something very interesting. Notice that in this expansion, you actually have that the temperature doesn't change, right? So what that means is that the energy doesn't change, right? So this is important. For an ideal gas, if you have an isothermal expansion, then the change in total energy has to be zero because the energy only depends on temperature, and temperature is not changing. Okay, so that is kind of the key of this isothermal gas expansion. With this, we can now go and apply the first law of thermodynamics, which is simply the change in energy has to be equal to the energy transfer as heat plus the energy transfer as work. Okay, well, if delta is equal to zero, what that means necessarily is that heat is equal to minus work. Okay, so here's how this works intuitively. It's very obvious that the system is doing work, right? Notice that we're pushing that piston from the systems to the surroundings using work, right? So what that means is that from that process in isolation, energy would be leaving the system, right? We're pushing that piston out, that requires energy, then that means that energy would be leaving the system. However, the energy doesn't change. The only way that this can happen is that at the time that you're losing energy as work, you're absorbing energy as heat from the surroundings, right? And then what happens is that if those two things are the same, then you will actually have that, you will get an isothermal expansion, and the change in internal energy will be zero. Okay, so that is where the change in sign comes from. Notice that the energy as heat is absorbed. Okay, so that will be positive. The work will be negative because you're losing energy to the surroundings, right? So you change the sign, and then you can reconcile those signs. Okay, so we can just try to apply this to a numerical problem, right? So if we use here that the atmospheric pressure, the external pressure is 1 atmosphere, and then your initial volume is equal to 10 liters, and your final volume is equal to 20 liters, right? The temperature can be anything, but we can say that this temperature is, say, room temperature, 298 Kelvin. Then we can start to work through this expression, say that, well, we know that in a gas expansion, the work is equal to the minus external pressure, change in volume, and then find that this number is equal to minus 1013 joules. And then what that means from that expression is that the heat absorbed is going to be equal to plus 1013 joules. All right, so that is how you get an isothermal gas expansion. You lose some energy as work, but the same energy that you lose, you transfer as work is being absorbed by the system as heat. Okay, and that's what those signs tell you. All right, so in this video we have seen a first application of the first law of thermodynamics to the specific case of an isothermal gas expansion.